Okay. Power to the power to.
So this is a brief introduction of my working place. I came from here through Bangkok, Kolkata, and Varanasi for 16 hours. Distance is 1,300 kilometers. Time lag 2.5 hours. Temperature is similar between Varanasi and Hsinchu, but I feel Varanasi is today hotter than Hsinchu city. And I got a PhD degree from the University of Tokyo in 2002, and I moved to the Okazaki Institute for Integrated Bioscience as a postdoc and spent there for 3.5 years. After that, I got a position in Tohoku University, Japan, and I worked as an assistant professor for nearly 11 years. After that, I got a position in the department National Charlton University in 2016, and after that, the university merged with Yang-Ning University, so now the name is National Yang-Ning Charlton University. That's wrong. And in our department of applied chemistry, there are nearly 35 professors and nearly 400 or 500 students. That's department. Okay, so far is my introduction. So let's start talk about spectroscopy. Okay. Now here is a photograph of the foods. It looks appetizing, strawberry or curry or some dishes, Indian dishes, current some. I like this. And only at a glance we can judge or it looks tasty, right? How about this? Appetizing. Maybe no. This is curry in Japan. No. So this is some character of anime, and this is I don't know how they prepare strawberry. And this is colored rice. We feel I don't know eat these dishes. Not appetizing. Why? Because it's blue. Okay, so hence color is somehow informative, right? So we get some information from color. Then, and so in our life we get the information from color. Then why not in science? We want to apply this consideration into scientific discussion. We want to use a color in chemistry. When we try to use color information in science, how can we experience color? Okay, here is green, probably you agree. Here is blue, probably you agree. Okay, then what is the color at this point? Okay, maybe blue-green. Then how about this intermediate? What do you call? I think this is blue, blue, green. Okay, this is blue, green, green, blue, 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 green. Okay, then what is these three lines? Dark blue, light blue, dark green, light green. So what? Anyway, we have no word to explain all the colors, continuous colors. For the scientific discussion, anyway, we need some objective explanation of the color is necessary. So we need to express some color in scientific manner. By the way, I found interesting website, so you can judge which color you judge blue, which color you judge green. This is in my case, I judge the right side green, left side right side blue, left side green. And this is the distribution of the number of persons who judge where is the border line between blue and green. Okay, you may check it. But anyway, I mean, explanation of color is the subjective. We need objective method to explain the color. For this purpose, we use spectrum. Spectrum is a plot of some parameter against wavelength or wave number. So this is the main topic of this talk. Here is a photograph of laser emission. Okay, it looks purple, it looks blue, green, orange, or pale orange, red. Okay. Again, there is no meaning to discuss what is this color. I think this is pale red, or this is pale orange. It's your opinion. There is no objective method. Okay, so what we need to do is to explain the color in objective manner. So let's plot intensity at each wavelength. Then we can say this line is not a purple, but the light having the wavelength of 405 nanometers. Okay, this is red color. Okay, but we should explain this laser beam in terms of 650 nanometer laser. So plotting the intensity against wavelength, then there is some peak, the most intense point. This is a representative number of this light or this color. So this is a very useful way to explain the color. Again, this is spectrum, a plot of parameter, in this case intensity, light intensity against wavelengths. We use spectrum for scientific discussion. So what is the origin of the color? There are three origins of the color. The first one is the absorption. Second one, emission. Third one, scattering. There are three optical processes. You know, absorption occurs when some chromophore absorbs the light. So we irradiate the light, then the chromophore in the orange part, beta carotene absorbs the light. Green part, chlorophyll absorbs the light. So some part of the white light is absorbed. Then the complementary color is exhibited. So it looks orange, it looks green. In this case, the energy of light is converted to the energy of molecule chromophore, electronic energy of the chromophore. This is absorption process. Second one is the emission. You may use this kind of fluorescence pen when you learn something. The mechanism of the exhibition of the color is different. In this case, the pigment does not absorb any color, but emits the color. Okay, so white light excites pigment in this fluorescence pen and drives the molecule into upper state. Then the pigment emits electronic energy and releases light. This is the emission. Fluorescence, luminescence belong to this group. So absorption converts light energy to molecular energy. Emission converts molecular energy to light energy. The third group, scattering, is somehow different from these two. So this is what we learn. This process is what we learn in today and tomorrow's talk. Scattering. scattering, in the case of scattering, light comes into the substance. Then, if nothing occurs, light passes through straight, goes away to somewhere. If some more optical interaction takes place, then the direction of the light becomes different. This is scattering. Okay? So today I will show the formulation for the Raman scattering process. The Raman scattering process belongs to this group. So let's learn about the scattering in more detail. We prepare the light source and irradiate through the sample. So here I prepare the green laser, blue laser. Okay, again wavelength is 488 nanometer. Then let's irradiate the sample. What color do you expect as a scattering light? Because we irradiate the blue color, scattered light should be blue, mainly blue. It's true. The intensity of the scattered light is distributed mainly on 488 nanometer, the same wavelength with the irradiation light. And when we examine other wavelengths very in detail, then we can find different color. So by multiplying 10 to the 5th power or 6th power, or anyway by expanding largely, we find the distribution, intensity distribution at different wavelengths. So this scattered light is very weak, but it's there. This is called Raman scattering. This effect is found by C.V. Raman in the early 20th century, and until today it is studied, continuously studied. Here is a photograph of the Raman scattering. So again, we irradiate blue laser, and main scattering is blue color. So by putting some filter, blue color is suppressed largely, but still this is main most intense scattering. And we see different colors, blue, green or red. This is the result of ethanol. We put ethanol here and irradiate 488 nanometer, and we can take this photograph by using digital camera. Okay? And different color occurs. Again, color is informative, so we can use the distribution of each color to study molecular structure. So here are 3 examples of Raman scattering photograph of 3 compounds, cyclohexane, ethanol, and water. We see multiple colors in the case of cyclohexane, and besides the excitation beam, the strongest line is green. Similar green line appears here and not here. And we know the green line occurs when the molecule involves CH bonding. So this is a CH stretching attributed to CH stretching motion. So that's why green line appears also in the case of ethanol and does not appear in the case of water. On the other hand, the red line appears when the molecule includes OH bond. This line is attributed to the OH stretching. That's why red line appears in ethanol, but not in cyclohexane. So the intensity pattern of the colors highly related to molecular structure. This photograph is convenient to check what is the difference, but we want to analyze in more detail or in more quantitative manner. So let's make it in the spectrum form. That is, let's plot the intensity against wavelength or wave number. Wave number is the unit of the energy, and we can calculate the energy difference from excitation beam. Each color has each wavelength, and the wavelength is converted to angular frequency, and angular frequency is related to the energy of the photon. So we can calculate the energy for each color. Then horizontal axis is the energy difference between the excitation beam and the scattered beam. Anyway, this is the Raman spectrum. We can explain distribution of the scattered light intensity against wave number or Raman shift energy difference. And Raman spectrum is different for each compound. So this is so-called molecular fingerprint. Okay, this pattern, intensity pattern, is different for each compound. So we can detect the difference of molecular structure, or we can detect the structural change by analyzing intensity pattern in detail. Again, there are multiple origins of the color absorption, emission, scattering, and in today's lecture and tomorrow's lecture, I will explain the formulation of the scattering process, and I will explain how to explain the generation of different color. Light comes into the molecule. Okay, it has a photon energy. A molecule has an electronic energy. Some interaction occurs. Then sometimes absorption occurs and intensity becomes smaller, or scattering occurs and propagation direction of the beam changes. Sometimes wavelength changes. Absorption, scattering, multiple optical processes are there. So we are going to understand what is the description of the generation of the scattered light. For this purpose, let's formulate what is light, what is molecule, and what is the interaction between them. So today's talk consists of 3 parts: the formulation of the light, formulation of molecule, and formulation of the interaction. Okay? So first, let's formulate the light. You know, light is an electromagnetic field. So when light propagates from left to right, electric field oscillates repeatedly. At the same time, magnetic flux density vector oscillates accordingly. And we accept an idea that these two vectors have the same wavelength or length in one period. Also, we know we have learned that the vectors of the electric field E. So we got write EK1, and direction of the magnetic flux density vector EK2 are perpendicular to each other. And these two vectors are perpendicular to the propagation direction, K. Also, we know there are no retardation between E and K. Okay? We may assume this knowledge as granted, but we should explain why, what is understandable explanation about these features. Sorry, some position is wrong. But anyway, E and B, vectors E and B of light should satisfy Maxwell's equation. So this is the starting point. So this is operator nabla. Nabla cross E plus delta B, delta T is equal to 0. This is the first line. Nabla by B minus 1 over C square, delta E, delta T is equal to 0. Nabla dot E, nabla dot B is equal to 0. So E and B should satisfy these four equations, fundamental equations. Okay, later please check some document about the definition of the inner product or outer product and the definition of nabla, this operator. We want to understand why E and B has such as many similarities or specific features, special features. And E and B are not separable. And we want to explain why they are not separable. So, to explain these features, we introduce another function, A. This is so-called vector potential as a common origin of E and B. Okay? We assume the operation to the vector potential A generates B. And considering the Maxwell equations, if we start from this equation, we successfully derive the vector E from A, like this. Excuse me. Okay, by introducing A, it's possible to explain B and E as a function of A. Oh, I should skip this. Then it's shown that the vector potential A is the solution of the differential equation, like this. And by solving this differential equation, we can assume a particular solution of A in this form as a periodic function, where the K is K has some requirement like this, and the length of the K, vector K is so-called wave number vector, and there is a requirement. The element of K should have a discrete number, and the length of K should be in proportion to the angular frequency omega or inverse of lambda, that is in proportion to the energy of the light. So the vector K is so-called wave number vector. R is equal to x by z in this figure. This is position vector. omega is equal to 2 pi nu angular frequency. Nu is a frequency in hertz. And based on this vector potential function, we can derive B and E. And in this case, considering some requirement for vector potential A, that is nabla dot A is equal to 0, we can assume any requirement for the vector potential A as far as E and B are the real number function. So we assume this relationship. This is so-called Coulomb gauge. And submitting to equation 11, we get nabla dot A is equal to this number, and it should be always 0. Then it leads to a conclusion that the vector A0 or the magnitude vector of the vector potential A dot K propagation direction is always 0. This is the inner product between A0 and K. That is, this relationship indicates that A0 is always perpendicular to K. So when we assume propagation direction of K is here, then vector A0 should be A0 is here. A0 should be perpendicular to propagation direction. So in this plane. And already we derived the vector E from A as equation 7. And substituting number 11, and we obtain the vector formulation of the vector E like this. It means vector E is always parallel to A0. That is, A0 is always perpendicular to K, and E is parallel to A0. So E is always parallel to vector K. And from number 5 already we know how to derive vector B from A. And from this equation, by substituting this equation, we see B is given by this equation. The vector B is parallel to the outer product of the vectors K and A0. That is, B is always perpendicular to A0 and K. K is this direction, E is parallel to A, and B is parallel to perpendicular to A and K. So from these 3 points, we see we can explain specific characteristic feature of the light successfully. That is, propagation direction is K, B and E are perpendicular to vector K. Okay. Now I'm formulating light to understand what is the origin of the Raman scattering, right? And one more question is that we want to formulate the energy of light. And the energy of light is calculated by solving the Schrödinger equation like this. And we see this form is the sum of the equations of the one-dimensional harmonic oscillator. The shape form is the same. So the energy of the light is calculated in terms of the energy of a one-dimensional harmonic oscillator. This equation, Schrödinger equation, is solved, and eigenvalue is given by this equation. Eigenfunction is given by this equation, including Hermite polynomial and normalization coefficient and exponential function. So considering the similarity, we can calculate the total energy of light and wave function as the sum of the energy of each component having different k and gamma. Sorry, I should add one more slide. Gamma indicates direction of the unit, polarization direction. Gamma is a parameter to indicate polarization direction. K is a wave number vector, so 1 means propagation direction is indicated by 1 and polarization is indicated by 1. The same propagation direction 1 and different polarization 2. So they are distinguished. Propagation direction k and polarization gamma. And different propagation direction k prime, different polarization gamma prime. So anyway, by summing up all the combination of k and gamma, we can calculate the total energy of light like this. Accordingly, the total wave function of light is calculated as a product of each eigenfunction. Okay? From these equations, we see the first line is the energy of light, and energy of light is quantized by quantum number nk gamma. Okay? This explanation is consistent with an idea that the energy of light is counted in terms of the number of photons. Second line, first line, the minimum unit of the energy is h bar omega. And again, this explanation is consistent with an idea that energy of photon is not only due to the magnitude of the wave, but also depends on the wavelength or angular frequency omega. In other words, it is consistent with Planck's photon hypothesis. So in these regards, this formulation is successful because this is consistent with the previous knowledge. And you see, energy and wave functions of light is explained, uniquely defined when we know quantum number of each component k gamma. In other words, all we need to know is the parameter nk gamma. Nk gamma determines E and psi uniquely. So it's possible to introduce such a truncated form. Total wave function of light is described by listing the quantum number of each component. This is so-called occupation number representation. Okay, you see it's more simpler than listing eigenfunctions for all the components or the total wave function is the product of the eigenfunctions listed here. So we may list normalization coefficient, element polynomial exponential function, coefficient polynomial exponential function. So we repeat this form, but instead it's possible to specify uniquely determine what is the wave function of total wave function of light by listing the number of photons. Then immediately we can return to the eigenfunction form by having these numbers. So this is convenient. So let's use this equation for further discussion. Then Raman scattering process is described like this. First, molecule exists in the state I, initial state. Light comes in. Some interaction occurs and system goes to N and immediately return to F. During this process, one photon drives molecule from this state to this state, and different photon drives a state from upper to lower final state. And this process is described by using the number representation. So the total wave function of the whole system as a product of the molecular part and light part. Psi is equal to I by light part. And intermediate state is state N and wave function in which the number of photons nk gamma decreases 1. And the final state that is not equal to the initial state. One photon decreases and one photon of another component increases. So Raman's, by using the numerical number representation, we can describe the Raman scattering process like this. Okay. So far we derived the formulation for the vector potential A, electric field E, and vector B like this, and energy wave function like this, energy and wave function of the light like this, and we accept a number representation, occupation number representation like this. We want to convert these equations from classical to quantum mechanical description. This formulation is based on the classical mechanics, but you know the event on the molecule cannot be described in terms of classical mechanics. We have to move to the quantum mechanics. So this classical description should be converted to quantum mechanical description. So this is what we do next. Okay. So again, what is the quantum mechanical description of AEB? This is the question. For that purpose, we introduce coordinate parameter large qk gamma that is equal to small qk gamma plus small qk gamma star. This is a real function. And we introduce a conjugate momentum according to this consideration. Then epsilon qk gamma that is calculated by substituting this equation into here, and P is also described by using small qk and small qk star. Then from these two equations, we derive equations for small qk gamma and small qk gamma star using large qk gamma and large pk gamma, like this. So far is the classical mechanics approach. And here we can introduce operator, momentum operator instead of momentum parameter itself. So let's substitute P with the operator and move to classical quantum mechanical description. So this is the qk gamma operator that calculates the magnitude of light. qk gamma is originally used as the magnitude of the repeating wave. Okay, qk gamma star appears here. And now we can introduce qk gamma and qk gamma operator and qk gamma T operator to instead of these classical parameters. Then, okay, this is the operator description of the magnitude of the light. And by introducing using qk gamma operator in this way, it's convenient. So by putting some normalization coefficient multiplied by qk gamma operator, we can derive such a convenient relationship. So normalization coefficient multiplied by qk gamma operator is defined as ak gamma. And when the ak gamma operator is applied to the wave function of the one-dimensional harmonic oscillator, then it is shown this operator changes quantum number of this wave function, -1. And the eigenvalue becomes square root nk gamma. Also, normalization coefficient multiplied by qk gamma t operator. This is defined as ak gamma t operator. When this operator is applied to the wave function of the one-dimensional harmonic oscillator, it changes the quantum number +1. And the eigenvalue is square root nk gamma +1. Then it is shown that by using ak gamma and ak gamma t, Hamiltonian of the radiation is described like this, in a simplified form. Also, by applying this Hamiltonian to calculate the total energy of the light to the wave function of the light, we can derive apply Hamiltonian shown by this equation, and we see eigenvalue is nk gamma and h bar omega k. So when we want to calculate energy of the light, we apply this Hamiltonian, and the total energy of light is given as a sum of nk gamma multiplied by h bar omega k. This is the photon energy multiplied by the number of photons. And this product is summed up over all the combination of k and gamma. This is a way to calculate the total energy of light, convenient way of to calculate the total energy of light. We can define the Hamiltonian by using the operators A and A dagger and applying Hamiltonian to occupation number representation of the light. We can derive total energy. Accordingly, we can replace Q and Q star with A and A dagger, AT. So, quantum mechanical description of A vectors A, E, B are given like this. So Q is replaced with A with some coefficient. Okay? Okay, this is the first part. We succeeded in deriving the formulation. We succeeded in formulating the electromagnetic wave like this. And we succeeded in deriving the Hamiltonian and wave function in the very simple manner. Okay? We have remaining two tasks. We have to formulate what is a molecule and what is the interaction. Okay, the description of the molecule is a little bit popular. Okay, molecule consists of the atoms and electrons. Okay, and each atom's electrons are allocated at a particular place. So we can regard molecule as a bunch of particles, n particles, of which mass is mi, charge is ei, position is ri, and I is from 1 to large n because it consists of n particles. In this case, the Hamiltonian to calculate the energy of this system is given by considering the contribution from kinetic energy and potential energy. It becomes like this. This is a very fundamental formulation. And for further discussion, let's assume that this Schrödinger equation is already solved, and He and electronic state labeled by small a gives the eigenvalue or energy Ea multiplied by wave function A. That's it. This is the formulation for the molecule. If there is no interaction, this is all we should consider in order to calculate the total energy of the system that consists of light and molecule. We can consider Hamiltonian for the radiation wave function of the light, Hamiltonian of the n-particle system. That's all. But as far as considering these two parts, nothing happens even if they meet. The optical process, including the Raman scattering, takes place because they interact with each other. So, third question is, what is interaction here? So finally, we should get some equation of the Hamiltonian to calculate the whole system. That should consist of a particle, molecular part, and radiation part, and interaction part. And this interaction term is calculated by considering the force that the charged particle go across the electric field and the vector B, vector E and B. Force is given by this equation. And E and B are, explained unifiedly explained by using vector potential A. So let's use A instead of EB and E. Then the additional term appears in the kinetic energy. This force gives additional energy in the kinetic energy part of the molecule. And this is described like this. So I skip the details because it becomes more complicated. So please follow some story. So without interaction, the energy of the molecule is explained by considering kinetic energy and potential energy. But in the electromagnetic field, kinetic energy is affected by the vectors E and B. And this effect is evaluated by considering this additional term. So this is the interaction term. So purple part is original Hamiltonian of the molecule. Green part is original Hamiltonian of the radiation. Blue part is the interaction term. So new Hamiltonian, including interaction term, should consist of three parts: particle, radiation, and interaction. And already we know the formulation about the particle and radiation. So let's derive interaction Hamiltonian H prime by subtracting these two from the total one. Then these two terms remain. Higher order term is eliminated because its contribution is too small. So large principal two terms appear like this. So from this formulation, we can say the interaction Hamiltonian can be separated into two parts. First one contains momentum operator P and vector potential A. So let's call it AP term. Second part consists of the square of the A. So let's call it A square term. Okay? So this is the last slide, just 1 hour. Okay? So in summary, in today's formulation, I explained, very briefly explained how to formulate incident light, how to formulate molecules as charged particles, and how to formulate interaction. Okay, so this is all I expected for the first 1 hour in today's talk. Okay, so I skipped many derivation step of many derivation steps of the equations. So you may ask me later. I try to explain as far as possible. But anyway, light has vectors E and B, and E as B, and propagation directions are perpendicular to each other. It's successfully explained. And these equations explains the energy of light is quantized, and it explained as a sum of the photon energy multiplied by photon number. And wave function is expressed only by listing the number, quantum number of each component. And this is a formulation of the Hamiltonian of the particle, charged particle. And interaction Hamiltonian is derived by considering the force that this particle feels in this field. And mainly, it consists of two terms. Okay, so tomorrow I will continue formulation of the Raman scattering by using these frameworks. Okay, so this is all for today's my first 1 hour talk. Thank you.